Hi everyone. Today we're going to be working through some problems with logarithms. I know it's been a little while since you've studied logarithms in depth, so this should just be a quick review for you. Hopefully it goes pretty well, but let me know if you have any questions. We're going to start out thinking way back to when we had equations like this. We had something like x squared equals 4. Well, when we had x squared equals 4, this was super nice because we know that 4 is a perfect square. And so we could actually solve this without really needing any math operations. We could say something like, oh yeah, well, if x squared equals 4, then x could be 2 because 2 squared equals 4. Or it could be negative 2 because negative 2 squared equals 4. And we're feeling great about that. But sometimes we would run into things like x squared equals 5. And we'd feel way less good about this because we couldn't think of a number that when you squared it, you got 5. And so what we did was we invented an inverse operation to squared. That inverse operation is the square root. And so we would say, well, x could be the square root of 5. Well, it could be the negative square root of 5 also. And this maybe was unsatisfying for you at first, but now that you've done square roots for a long time, you've come to realize that, oh yeah, this is some number, and I have a sense that it's some number a little bit bigger than 2, not quite 3. This is going to be the same principle that we have with logarithms. If instead of x to the second equals 4, we had something where 2 to the x equals 4, again, we feel pretty good here. 4 is a power of 2. So that just means, oh, 4 is 2 to the second power, so x had better be 2. And this was all well and good when things were nice and simple like that, but when we switched things to the x equals 5, suddenly we didn't know what to do anymore. And we're at a point where square roots don't really help us solve for exponents, so we have to invent a new operation, the inverse operation of exponentiation, which is called logarithms, right? So in order to solve this particular problem, I'm going to invent something new, and it's going to be called a logarithm. This is going to be log base 2 of 5, and that's going to be my answer there. The key to understanding logarithms is just what we've done here. Logarithms are just inverses of exponents, and if we use the right terminology when we're saying a logarithm out loud, it helps us remember what's going on here, right? If we remember first, logarithms tell us about exponents, then we know that when you have a logarithm expression, it's equal to your exponent from your original expression. So that's a really good thing to remember. Second, if you have a logarithm, you would say this, log base 2 of 5. Because you're saying base 2, it reminds you that in the exponential equation, 2 is the base. So if we know where the exponent is, and we know where the base is, then we can always rewrite a logarithm as an exponential equation and try to figure out what's going on. Let's do a quick example of that together. I'm going to start with a log equation. I'm going to rewrite it in exponential form. So here we go. If I have log base 3 of 9 equals 2, here's what I remember. Log base 3, that means 3 is my base, of 9 equals 2. We remember the logarithm gives the value of the exponent. That means 2 is our exponent, and that should be 9. Okay. We can have our base be anything we want, just like when we took radicals. We could take a square root or a cube root or a fourth root. We could have the index be whatever we want. Same thing here with logs. Now, let me show you one last thing really quickly. As it turns out, if you go and study some more mathematics, you will see that the base that we most commonly choose is the number e. E is just some number. It's about 2.7. And if you wanted to keep going, you could. It's irrational, just like pi. It's got lots of cool properties, and we won't delve into why we choose this as our base, but we call it the natural base. It just arises as the base that makes the most sense the more you do mathematics. So if I had 2 to the x equals 5, and I wanted to solve this, I might equally, instead of using log base 2 like I just did, choose log base e. And we have a special name for log base e, it's called the natural log. I could just take the natural log of both sides and get this. Alright? Here's where we get into a bit of a gray area because I still haven't solved for my exponent, so maybe we'll chat for just a moment about properties of logarithms and see what happens here. I'm not going to prove any of these properties. I'm just going to use some examples to give you your intuition. So let's say I had a log base 2 of, I don't know, 4 to the third power. Okay, and I want to know what this equals. Well, if I think about it for a bit, I can come up with a few things, right? 4 to the third is just 64. And this is saying my base is 2. What exponent do I have to raise 2 to get 64? And the answer is 6. So this answer is 6. So far, so good. I could notice that things build up in this nice way where if I had log base 2 of 4, that's equal to 2. And I noticed that log base 2 of 4 cubed is equal to 6. So I come away with this nice generalization. If I have log base b of a to the x, that's equal to x times log base b of a. Again, this is not a proof. It's just a quick example to illustrate this property. If you want a proof, chat with me after class. I'll show it to you. But for right now, take my word. Hopefully this example helps encourage you that this is true. So why is this helpful? Well, it's helpful here because if we wanted to solve this for x, we could now use this property and pull this guy out in front and solve it for x. And doing this would give us x times ln2 equals ln5, so divide both sides by ln2, and x would be equal to ln5 divided by ln2. Okay, and that's kind of cool because this equation that we started with here gave us this example as the value of x, and it also gave us this as the value of x, which means these two values must be the same. In fact, if you have log any base of some number, you could rewrite it in terms of natural logs. Natural log of 5 divided by natural log of 2. This is called the change of base formula, and we almost always change into base e because e is where it's at. And now we're going to move slightly into some calculus here. So we're going to start out with some logarithmic functions and see what happens. I'm actually going to leave this up on the board. Let's say we wanted to know what's the derivative of natural log. Well, you might already know that this is 1 over x, but let's say you didn't know what it was. Let's say it's equal to y. We don't know what y is, but that's okay. So let's take a step back, actually. Let's not differentiate right away. Let's say natural log of x equals y. Well, remember that this is log base e of x is equal to y. That means the same thing as e to the y is equal to x. And if I wanted to, I could now differentiate both sides with respect to x. And this would tell me, well, the derivative of e to the y, which we've seen lots, is just e to the y, but it's times dy dx by the chain rule. And the derivative of x is just 1. Not too bad so far. Well, what would we do next? Well, our goal, right, was to solve for dy dx. We wanted the derivative of this guy. So how can we do that? Well, e to the y is equal to x. We know that from this previous step, from just rewriting this logarithm equation. So that means that x times dy dx equals 1. And that means that dy dx equals 1 over x. So the derivative of natural log is just 1 over x. That's pretty nifty. We can use natural logs, now that we know their derivatives, and apply them to equations like this one. Except if instead of using bases of e, we can use any base and we can kind of figure these things out. So let's try to do a couple examples of logarithmic differentiation here. Let's say we had a particular function, and that function was maybe y equals 2 to the x, right? And we wanted to differentiate this, okay? So I could do that. So dy dx should be the derivative of 2 to the x. Well, that wasn't very helpful now, was it? Not really. Maybe what I should do instead is try to transform this, right? I don't know how to take a derivative if the base is not e, right? When the base was e, we knew that it was e, and we showed this using the definition of derivative. But when the base is not e, I don't know quite what to do. So what I'm going to do instead is, since I know the derivative of natural log, and logs solve for exponents, I'm going to take the natural log of both sides. This tells me that natural log y equals natural log of 2 to the x. And this is really nice because I just showed that there's this property of logs where you can bring down exponents out in front. And ln2 is just a constant. It's saying, what power do I raise e to get 2? Since e is 2.7-ish, this is a little bit less than 1, but that's okay. So now I'm going to go ahead and use my derivatives. If I'm going to take the derivative of both sides here, the derivative of ln y is 1 over y times dy dx. Remember, dy dx is what I'm looking for. On the right-hand side, the derivative of x ln 2, remember this is just some number, so this is just a linear function with slope ln 2. So its derivative is ln 2. Well, that means that dy dx is equal to y ln 2. But y was just 2 to the x. So we get our derivative is 2 to the x ln 2. And you can see that I can replace this 2 with any number I want, and I'll always get this same procedure out, as long as this number is positive, because if it's negative or 0, I can't take the natural log of it, right? Okay. So here's the rule that I get, the general rule. The derivative of a to the x is equal to a to the x times natural log of a. And maybe you're wondering, hey, if a is e, how come this doesn't work? A twist, it does work, right? Because the natural log of e says, what power do you raise e to get e? And the answer is 1. So maybe some quick facts about logs would be good. Things that you should absolutely know no matter what. You should know that the natural log of e is 1. Definitely always should know this. You should also know that the natural log of 1, well, that's saying e to what power is 1? That answer is 0. These two facts are fundamental. You have to know them. They are super important. And if you know this property here, that if you have an exponent, you can bring it down in front, you can figure out things like, oh, what's the natural log of e squared? Well, it's just twice the natural log of e, and natural log of e is 1, so natural log of e squared is just 2. As long as you can continue to say to yourself, log is telling me an exponent, you should be in good shape to understand what the log function is trying to do. We're going to do actually 2 more examples here. One more that's a little bit more complicated than these ones, and then one that involves integration instead of differentiation. So let's get to it here. The thing about logs is that they work really nicely, not just when exponents are x and bases are real numbers. In fact, if we had a more complicated function, for instance, y equals sine of x, and I was raising this to the power of cosine x, I could totally do this if I wanted to take the derivative, this is what I'm saying here. So let's take the derivative. Well, I have no idea how to take the derivative of this. It's a function raised to a power of another function. So instead, what I'm going to do is the same trick as last time. I'm going to take the natural log of both sides. I want to bear in mind here really quickly, not as a main point, but as a side note, that this only exists when sine to the cosine is positive. Now I'm going to just keep going just like I always do. Since I have a power on my base here, my property of logarithms says that I can pull that power out in front. And now I'm all set to differentiate because I know the derivative of cosine, I know the derivative of natural log, and I know the derivative of sine, and I just need to remember to use the product rule. So let's differentiate both sides. The derivative of ln y, which we've seen a few times now, is just 1 over y times dy dx. Product rule says derivative of the first times the second plus the derivative of the second times the first. So derivative of the first is negative sine times the second, which is ln sine, plus derivative of the second, which is 1 over sine, times cosine. This is chain rule for this. And then I'm going to multiply by another cosine. Whew, that's getting long. I can condense this a bit, because cosine divided by sine is cotangent. And I'll multiply both sides by y, and I'll get negative sine ln sine plus cotan cosine. And last but not least, we recall that y is equal to this guy, so we just go ahead and replace y with sine of x to the power cosine of x. And then we still have times all of this stuff. Sine x, natural log sine x, plus cotan x, cosine x. Yikes, that's my derivative. Pretty long, but pretty manageable, as long as, one, we recognize that anytime you have a function raised to a power of a function, we need to take the logarithm of both sides. And we'll choose the natural logarithm because it has the nicest derivative. And two, we keep in mind the power rule of logarithms, when if there's something in here raised to a power, you can pull that power right out. Those are the two big things that we have to remember to solve this problem. And this works for any problem when you have f of x to the power of g of x. In fact, an early problem set had you do this without functions given, just literally f of x to the power of f of x, I think was the particular example. And you can come up with a formula in general for that if you'd like to. And that was all differentiation. More recently, we've been doing integration. So let's think about, what if I had the integral of a to the x dx? Right, how would I integrate this? Well, fortunately, right here, I have written the derivative of a to the x is a to the x times natural log of a. Well, what's interesting is that we know that integration is the inverse operation of differentiation, so I can kind of do this little trick right here. If I integrate both sides here, and of course I'm integrating with respect to x, the integral and the derivative, whoop, they're gone. I just get a to the x. On the right-hand side, I get the integral of a to the x times ln a dx. But what's cool here is that this is a constant, So I can pull it right out in front. A to the x is equal to natural log a times the integral of a to the x dx. And since this is an equation and this is just a number, I can divide both sides by ln a. And I get a to the x ln a equals the integral of a to the x dx. Of course, we have to remember the plus c if we're taking an integral without bounds. So let's just write that to be precise. This is going to be a to the x over natural log a plus c. Great. If you ever forget integrals, but remember the derivatives, you can always use this trick. Always. You can integrate both sides and then rearrange some things and everything will work out pretty nicely. Okay. So let's just do one last example here with some numbers in for area and see how it goes. If I asked you to take the integral from e to pi of 3, maybe I'll make this up. No, I'll keep this upper bound pi. Of 3 to the x dx. Well, I've now derived this. So I get this nice formula. It's 3 to the x over natural log 3 from e to pi. And that's going to be 3 to the pi over ln 3 minus 3 to the e over ln 3, which is just 3 to the pi minus 3 to the e over ln 3. And there you have it. Not the worst, not the best maybe, but at least hopefully understandable. And if it wasn't, you should seek me out and let me know, and we can chat in more depth here. But this was a reminder and refresher of logarithms, both from Algebra 2 with the very intro there, and from calculus. And hopefully you're feeling a bit better about logarithms now. So best of luck as you review.